Alright, so this is section 6.2 where we're looking at enthalpy and calorimetry and still talking about energy. So let's look at enthalpy first. It is energy plus pressure times volume. Okay, we went over this in class, but this is just for a quick review. This is abbreviated with H, so H is equal to energy plus pressure and volume. As long as we keep the pressure the same, because we're looking at the change in enthalpy, we are also looking at the change in energy and the change of temperature and volume. If we keep this the same, it goes away. Okay, it's not something that we have to worry about. So we can say the change in enthalpy is equal to the change of energy, which we can say equals the heat of the reaction. Okay, so one way that we can measure the heat of a reaction, whether it's heat is generated or heat is consumed, is using a calorimeter. And we'll do this in class on Tuesday. But to do this with a calorimeter, we usually use water. And to use water, we have to know how much energy it takes to heat it up or cool it down. Okay, so what we're going to look at is the amount of energy, which is joules of energy, it takes to heat any liquid up 1 degree Celsius. That is known as the heat capacity of that liquid. Alright, if we do the amount it takes to heat, the amount of joules it takes to heat some 1 degree Celsius grams wise, that's called the specific heat capacity, and it is abbreviated S. And if we do it with moles, it is the molar heat capacity. Alright, so when we plug this into an equation, what we find is that energy is equal to the specific heat of the liquid times the mass of that liquid times the change in temperature of that liquid. Excuse me. Okay, so that's the formula we're looking at. So let's put it into a couple of problems and look at it. In the back of the book, we're going to look at problem 43 and at problem 45 for this one. So 43 first, and I will read that. It says, a 5-gram sample of one of the substances listed in table 6.1 was heated from 25 degrees Celsius to 51.1 degrees Celsius, requiring 133 joules to do so. What substance was it? So if we look at our calorimetry formula that we just saw, we see that energy is equal to mass times the specific heat times the change in temperature. Alright, well the energy that this one put out, it said, was 133 joules. Okay, so that's what that one was. It said that it was a 5-gram sample, so I know I have 5 grams. I want to know what it is, so this is going to be my exponent. And the change in temperature is going to be my 55.1 minus my 25.2. Okay, so we can just take, so when we do that, this is 29.9. If we divide that across to this and divide this across to that, we get a 0.89 joules over grams times degrees Celsius. So that is a specific heat, is equal to S. When we look at the table, that is aluminum, specific heat. Problem number 45, sorry I got a little bit of a runny nose, I'll stop sniffling here because it's kind of gross. Problem number 45 reads, a 30-gram sample of water at 280 Kelvin is mixed with a 50-gram sample of water at 330 Kelvin. Calculate the final temperature of the mixture assuming no heat lost to the surroundings. This one has two tricky parts to it that once you understand makes this a lot simpler. First, energy cannot be created or destroyed, right? So I have the energy equals ms delta T of my cold sample and the energy of my ms delta T of my hot sample. Well, my hot sample is going to give energy away. My cold sample is taking that energy, right? It is going from one to the other. It doesn't just disappear somewhere, it has to flow somewhere. So it turns out that these two energies are the same thing. So instead of setting them equal to that, I can actually set them equal to each other. So my mass of my cold water times the specific heat of the cold water times the delta T is equal to the mass of the hot water times the specific heat of the hot water times the delta T of the hot water. I can even go a step farther. They're both water, so I can get rid of the specific heats. So the mass of the cold water is equal times the change in temperature of the cold water is equal to the mass of the hot water times the change in temperature of the hot water. So let's throw the mass of the cold water in here, which is 30 grams. Okay, it is going to go, you have your temperature initial minus your temperature final there. Right? That's the change in temperature. Whatever you have initially minus what you have finally. The mass of the hot water was 50 degrees, or 50 grams, sorry. And it too goes from final to initial. Alright, sorry, I gotta fix something real quick here. I just thought of. When you're setting this up, you always want your change in temperature to be a positive number. You don't want to work with negative numbers. So when I have my cold temperature, I want to start with my temperature final minus my temperature initial, because that will be a positive number. Okay, because my hotter temperature, my final temperature, is going to be bigger than my lower temperature. So we're not going to use that. When I do my hotter to colder, I want to start with my initial going to my final, so that I always have that positive number in there. Okay? So let me rewrite that. We're going to have 30 grams times my temperature final minus my temperature initial is equal to 50 grams temperature initial minus temperature final, so that I always end up with a positive number in the change in temperature. Now the second thing that we're going to look at and we're going to think about, my hot water is going to a final temperature. My cold water is going to a final temperature. So those two temperatures are also the same temperature. Okay, so if we can narrow that down, if we solve for that, that will give us what we're looking for, the final temperature. So I know that my 30 grams started at a temperature of 280, and I don't know what, oops, got that backwards, sorry. I don't know what my final temperature is, but I know it started at a temperature of 280. My hot one started at a temperature of 330, and I don't know what my final will be on that. Okay, so if I punch everything through, I get that I have 30 temperature final minus 24 8400 is equal to 16,500 minus 50 temperature final. Alright, so I can take my temperature final across, and I can take my 84,000 across, and I get 80 temperature final is equal to 24,900. Divide that by 80, and my final temperature of that solution will then be 311 Kelvin. So there is section 2 for you.